Hello, today we're going to talk about the influence of datasets. This is the seventh talk in the interpretable NLP series. As an motivation, there are many data points in each dataset, and the data points are definitely not equal. Some of them contribute to the models the most. So to start with, we want to look at how much influence of each data sample. How much does a data sample influence the output of the model? So if we change the input, how does the model that is trained on this data set changes? So there are many ways to see this sort of surprisal. For example, we look at the activation or the logic values or the gradient magnitudes, or we see if the predictions of the final layer changes, etc. One of the methods is called input marginalization. This is a generalization of the input perturbation method. So previously, the input perturbation refers to changing the tokens to another values, but the input marginalization considers all possible alternatives that you change these tokens into. So instead of removing this token, they change this token to a collection of all possible alternatives and take the expectations of the result. So this is a motivation. Let's start to formulate the influence of the input to the output and to the models. The influence function is an early attempt to understand the black box predictions of the models. So let's first write the data points as z equals input x and output y. On this data set, let's train an empirical risk minimizer, theta. Theta minimizes the loss function, L. So now we upweight a training point z by epsilon. Let's look at how the loss L is impacted by this operation. Essentially, we want to approximate the gradient, the derivative of L towards epsilon. So L is computed using theta, and theta is minimized on this dataset, and this dataset contains an upweight training sample, and this sample is upweight by epsilon. So this is a chain of impact. So this is not very easy to compute, but there are some ways to mathematically write down this rigorously. So they defined the influence function I as the derivative of L against the epsilon, taken when the epsilon is equals to 0. So following the standard derivation, this equals the this can be written down as the using the Hessian and the gradient. So this is from the Pangwei's original slides in 2017. Also in the slides, they mentioned several potential issues. The first one is the computational inefficiency. So although there are some methods to accelerate them using the when computing the inverse of the Hessian and the gradients together, the overall computation efficiency is still pretty low. Also, there are some non-smoothness in the loss, and there are some difficulty in finding the global minimizer. So theta, as we remember from the previous slide, is assumed to be the global risk minimizer, but empirically, finding this globally minimized. Finding this global minimum is not always possible. Regardless of the potential issues, this influence function has wide application perspectives. One of the applications is by Brunet et al. 2019. They used this to understand the origin of bias in the word embeddings. They studied the Glovac embedding, and for the loss, instead of studying the cross-entropy loss, they took the word embedding association test score. This measures how biased a word embedding is. So using this setting, they can compute the influence function that traces the contribution of each text input towards the bias score. So in this way, they can figure out the origin of the most biased word, or origin of the words that contribute to the bias the most. In 2020, this paper from CMU connected the influence function towards the dataset superficial or spurious correlation features. We found that the items with the highest influence scores do affect the classification performance the most, and these explanations are consistent with the explanations from the gradient-based saliency scores. So the highest, the samples with the highest influence scores also have the highest gradient-based saliency. And also, they studied the Hans dataset samples. They found that Hans samples with the highest absolute values of influence scores also tend to have the highest lexical overlap rate. And they consider the lexical overlap rate as one of the spurious correlations. Regardless, almost all the data samples have small absolute values of influence scores. So let's look at another method to study the data set. So Wallace in 2019 found that if we change the data set samples by only slightly, by, for example, adding a trigger that is almost does not make too much sense to humans, then we can effectively toggle the model predictions by a large margin. In the sentiment analysis example as shown in this table, we add 3 words to the front of the sentences and found that the model predictions are toggled from positive to negative. These are called the universal adversarial triggers by the authors. So we should, the moral of the story is that we should understand more of the data sets, and we can do some modifications to the samples, and this might give surprising results. In 2018, Ribeiro tried to find the several if-then rules that the models are anchoring on the predictions. So an anchor is a set of predicates that returns 1 if all of its feature predicates are true for this instant x. So let's say x contains 10 features, and a of x considers the first 3 features. If the first 3 features are all equal to positive 1, then a of x returns 1. In other scenarios, a of x returns 0. So they consider the precision of a. So ideally, the anchor a has very high precision. So whenever a is positive 1, then we can predict with high confidence that the model output y is about 1. So there is a probabilistic definition. So when the when we see a when we see a is larger than some value, then there is a probability that it's the model's precision is larger than 1 minus delta. Okay, so effectively they toggle this into a combinatorial optimization problem. So they select a combination of the features, and if multiple features, collection of these features meet this probabilistic definition criterion, then they choose the one with the highest coverage. And the coverage is the probability that this collection of features are widely applicable to the samples. So let's say if there are a collection of text corpus and we are studying the, for example, collection of emails, then one feature is about the occurrences of the stop word to, and the other feature is about a very infrequent word, let's say toggle, then feature one has a wider coverage than feature two. Now let's get to a theoretical framework. Adversarial examples are not bugs, they are features. They consider a binary classification problem setting. So the labels of each data point could be either positive one or negative one. Let feature be f. So empirically, f corresponds to the input towards the softmax layer. So they multiply the f with label y and take their expectations. So if this feature is highly correlated to the labels, then this expectation is high. So they say that this feature is row useful if this expectation is larger or equal to row. Additionally, they consider the adversarial perturbation. So they add a perturbation, a delta, that is, for example, that is limited in the limited by its L2 magnitude, like 0.001, and this perturbation can point to all sort of different directions, and there is a direction that is the most adversarial. So f of x plus delta correlates to the label the least, and even in the least correlated case, the expectation is smaller than is larger than gamma. Then this feature is gamma robust. So these two definitions are very useful for telling apart whether each features are robust or not. So this, I think this theoretical framework is an interesting one. Also in that paper, they attempted to train a robust classifier and also use this robust classifier to generate a robust version of a dataset. So this part is more controversial than the previous of theoretical definitions, but I'm going to just include them for the completeness of this introducing this paper. So a robust model will minimize the cross-entropy loss under adversarial perturbation. The goal is to construct a dataset whose features are relevant to those of the robust model. So how do they construct the dataset? They sample some points from this dataset, and then they try to find another another feature set x prime, so that the starting from x prime, they try to optimize towards z. Z is a new data point, and looking from the perspective of the robust model GR, z and the x produce almost the same representations. So the features produced by these 2 points are close to each other in terms of L2 distance. And this is solved with a normalized gradient descent starting from x prime. And after that, they add this z with the corresponding label to the so-called robust data set. So there are some controversy about this method because essentially this considers both the robust features and the non-robust features. But this is still a nice attempt to try to collect a robust version of a data set using the robust model. And I think this framework is one of the earliest methods to allow automatic analysis or automatic disentanglement between the robust versus non-robust features. In 2020, the dataset cartography paper is a nice attempt from another perspective to analyze the datasets. Instead of looking at each individual features, they looked at all the features collectively, but they look at individual data samples. They study the training dynamics of the data samples. They compute the variability and confidence. Using these two scores, they can plot the data samples onto a graph where the variability and confidence are the mean and the standard deviation of the correct label probability at each epoch. So throughout throughout the training processes, there are, for example, 10 epochs, and therefore there are 10 scores. So they took the average of these 10 scores to get the confidence and took the standard deviation of these 10 probabilities to get the variability. So if the confidence is high and the variability is low, then this means that the true label probability is high throughout the training process. So this corresponds to the easy to learn section. So they found out that the easy to learn section is correctly classified most of the time. So to the contrary, there's a hard to learn region where the confidence remains low and the variability is small, and therefore the correctly classified percentage is small. And for those dataset samples that involve a lot of variability in the training, this means that the model predictions throughout the training process is varying a lot. So the model is not that sure, neither is the model that unsure about whether these data samples are correct or not. So these are the ambiguous samples. So in this way, they sort of classified or cluster these data sets into easy to learn, hard to learn, and ambiguous domains. This is the dataset cartography paper. Another interesting paper to analyze the dataset is the distributed Shipley. So in comparison to the original Shipley paper, which studies the Shipley value on the whole dataset, they studied the Shipley value based on only a collection of a subsample of the dataset, and they take the average of this subsample. So theoretically, they are so intuitively they are almost the same thing, but theoretically, this definition of the Shipley value has various theoretical benefit and also empirical benefit as well. Dataset condensation is the last paper that I want to introduce today. This is just accepted to iClear 2021. So given a training set T, they want to synthesize a small set of informative samples S. There are many iterations in doing that. So for each iteration, they train two models, one on T and one on S. They want to minimize the divergence between these two samples, between these two models. And the way is either match their parameters or match the gradients. There are more details in the papers that are linked in. There are more details in the papers about matching the parameters or the gradients. So they repeat these above steps until stopping conditions. So after these iterations are done, they collect a small set of informative samples. So on this set of informative samples, it is possible to train a model that resembles the models that are trained on the original set. Either their parameters are similar or the gradients are similar. So this is effectively a condensation of a data set. In this paper, they also compare it to some traditional dataset selection method, like the core set method. So in summary, we briefly look at some papers that involve perturbing the samples or analyzing how this perturbation affects the model performance, aka inference functions. We also look at the anchors and the features and adversarial examples. And at last, we look at some papers studying and refining the dataset.